Hello and welcome to lecture 9, where we're going to come back for a second to chaos. You asked me a lot of questions. How does chaos happen? And so I thought, let me come back and revisit that just so maybe it will add a little bit more understanding of this really fascinating topic. So now we are in part 1 of lecture 9. Chaos. Transition to it. How do we get there? Roots to chaos. So if we recall back how we got to chaos, that was on an example of a driven, damped pendulum. And this chaotic oscillator was basically giving us a continuous mapping between the initial conditions, theta and theta dot, and into theta and theta dot at a later time. So this was at initial time, got mapped into a later time. But it is useful to consider the system not in this continuous remap mode, but rather in a discrete mode. So for instance, we could evaluate the system at time t, whatever time you picked, t plus a period of our driving force, t plus 2 periods, t plus n periods. And why is this interesting? Well, that's because once the initial conditions are forgotten, then the only thing that changes is the initial forcing, the external forcing or the external driving that is shaking up our oscillator. And in this case, the beginning of every period is just as good as any other period. And so that is the idea behind the Poincaré section. Each period is equivalent to another one. And so what we're going to do is use that in order to reduce a continuous chaotic system to a discrete one. So how will we do that? Well, we've actually done that before, and the way we did it was we evaluated the state of the system once every period, and we picked the initial time to be the beginning of the period. So we always evaluated the system in the same phase. You can think of it as, looking at the behavior of weather on Earth on January 1st every year. Instead of bothering with the seasons changing, we on Earth are driven periodically by its orbit around the sun. So if we forget about that and just evaluate the weather on January 1st every year, well, that takes away the worry about what's happening during the period. And so that's kind of what Poincaré's section does to us. So let us now get a better sense of how this continuous remap, the continuous behavior of the system, connects to this discrete representation of the system once every period. And for that, I made a few 3D movies, which hopefully will give us some intuitive understanding of what's going on. For that, I will need to clean this board a little bit to open up some space, and then that will help us to look at the movies. All right, we're done with cleaning the board. Let me make this into 9.2, just to reflect the fact that we've had to raise the board. And now we have switched to the next stage of this lecture, which is the movie stage. All right, so this is going to be pretty cool. What we're going to do first is we're going to take a look at a non-chaotic oscillator, a period 1 oscillator. And let us recall what that is. So if we were to draw a Poincaré, sorry, actually not Poincaré. Poincaré will be a bit later. If we were to draw a bifurcation diagram, so that will be theta as a function of the amplitude of the driving force. Then for a driven oscillator with the following parameters, with omega d equal to 2/3, with q equal to 1/2, so that's the driving frequency. This is the dissipation parameter, with g over L equal to 1 for simplicity, so that omega squared, the natural frequency, squared will be equal to 1. And with the standard initial conditions, 0.2 for the initial angle, and 0 for omega. So these are the parameters of our pendulum. So for these parameters, if we were to compute a bifurcation diagram, we're going to get something like that. So around the driving force amplitude of 1.4, we're going to get a period 1 system. That means that our system has a single period. The period doubling hasn't yet happened, so that every time the force goes through a period, our system responds in exactly the same way. So the system is completely reproducible. It mirrors the behavior of external driving every time in the same exact way. If we go to the higher amplitude of the driving force, 1.45, then we're going to experience period doubling. And in this case, we're going to get a period 2 behavior, where once a period, the system will do one thing, and in the next period, it will do another thing. So one period it does one thing, the other one the other thing, and then it comes back. So it cycles between 2 states. So it kind of has more choices. And then finally, if we go to the driving force of 1.5, then we are going to get into chaos, where there are just so many of these states that the system keeps choosing a new one every time, and you kind of don't know which one it will pick. And so that's what is chaos. So many of these period infinity state, basically, where every period of the driving force, our system reacts potentially differently. And so let us go over one by one, and let's take a look at a 3D illustration of this. So this is what I have prepared for us. So let us take a look at this one. So this is period 1 system, so it will be exactly periodic. And so what you can see is this is the initial position of our system. This way goes phi, so let me draw that. So our trajectory will start over here, and it will go around in a circle and come back over there. So that will be our phase. It goes around the circle. Now, I will erase that. We will actually see how that works. And what else you can see here is you see this sort of rectangle, and this rectangle is actually showing you a Poincaré section, or what will be a Poincaré section. So this is going to show omega plus pi. So the this is going to be, the middle will be omega equal to 0. To the right it will be positive, and to the left it will be negative. So this is minus pi, and this is plus pi for omega. And this is theta. In fact, this bottom left corner will be theta equal to minus pi, and that upper left corner is plus pi. So omega goes from minus pi to pi, and theta goes from minus pi to pi. So this is a Poincaré section, perhaps transposed. Typically, omega is along the y-axis, and theta is along the horizontal axis. I did it this way just so that time or theta goes up, because then it's kind of easier to imagine that time goes up as opposed to the right. And why I do that is because this little particle will be tracing out kind of circles around here. So let's see how it goes. So let me play this movie. So here is our system following a trajectory. At this point, our theta jumps, it wraps around, and so that's why it kind of comes out from the bottom and comes back from the top and continues going around in this kind of circular pattern, or rather periodic pattern. And because this is a period 1 system, nothing is changing. You can see that the system continues tracing out the same exact path over and over again. So this is pretty clear that our three-dimensional space of our system, right? So this is phi, that is theta, and this is omega, gets mapped into this two-dimensional plane, which is happening at phi equal to 0. So this is phi equals to 0 plane. So at other phases, we will have different positions of our system in terms of theta and omega. So you can see that our system is tracing out this weird figure if we were to keep track of it in theta omega plane all the time in all phases. But if we only evaluate it at one single phi equals 0 phase, then we're going to get just one single point. And that's what Poincaré section does. It evaluates the system only at one point. And so what it does, it checks. Is it still the same after one period? Yeah, okay, fine. It's still the same. And so this little yellow dot is an indication that nothing has changed. Our system is period 1. It's always the same. Every period, it does the same thing. All right, so now let's go to a period 2 system. How will that be different? So again, this is our initial condition. In fact, it's actually state of the system 9.5 periods after the start with these initial conditions. So let's try and do that. And then I run this for until 200 periods. So start with 9.5 periods, and then run until 200 periods. And starting with period 10, we're starting to see what sort of contributions to Poincaré section will be happening. So let's run our system and see what happens. So you see that we've completed one period, and the second one is not the same. So you see, this is what happens with period 2 system. Every time it completes one orbit in this theta omega space, it comes back but along a different path. And so you can see that it's jumping from one path to the other every time it is going into the next period. Every time it completes an orbit, it hops from one path to the other, of course, smoothly. And if we keep running the system, the same thing will keep going and going and going forever. So we see that the system comes in, goes through our phi equals 0 plane. This is our state of the system, and then it hops over to this one. And the system hops between just 2 points in the Poincare section. So this is a period 2 system. If we were to go to period 4 system, there would be 4 points on this plane, and so on and so forth. But let me skip over and go directly to period infinity system or chaotic system for fd equals to 1.5. So that's our state of the system after 9.5 periods from the initial conditions, and let's get it started. So you see that we've gotten one contribution to Poincare section. The next period came in on a completely different trajectory. And the other one comes and hits in a third point. So what we're doing is we basically are hopping between all of these different values of theta in this Poincare section. And so every time we're going to hit a new point, because the system is chaotic, it's picking one state of the system out of an infinite number of states. So that's why we are going to trace out a trajectory. It's a strange attractor, and by strange, when we say strange, we mean it's actually fractal. So if you keep zooming in onto the structure that's currently developing, we're going to see more and more substructure. And if we zoom in onto that substructure, we're going to see even more. Of course, in order to see substructure, we will have to run the simulations for a very long time, because the longer we run, the more points in this cross section, in this Poincare section, we're going to get 1 point per period. And so what I'm doing here is I'm showing the old holes that our trajectory punched through this Poincare section at phi equals 0 with the orange dots, and the last 2 ones I'm showing with the yellow dots. So you can think of these yellow ones as grapefruits, and all these orange ones as oranges. So the grapefruits are the last 2 hits that our Poincare section has experienced as the orbit passed through it. And so what happens is that this is the last one, the last one, and then now this is a new one. So what these grapefruits are telling us is the mapping that is a discrete mapping from one beginning of the period to the next. So instead of a continuous mapping from t equal to 0 to the current time, we are going to get a discrete mapping from t equal to 0 to t plus td, t plus 2 td, and so on. So we're going to get a discrete mapping. So by going from a continuous system to discrete one, we are going to simplify it. We're going to look at just this one cross-section that removes all of the rest of the complexity. As you see, the system would have traced out all of these complex curves in this phi equals 0 plane if we kept evaluating it at all the values of the phase. But what we do instead is we evaluate it only at the times that our 3D trajectory makes a hole, punches a hole in our Poincare section. And so what we are getting is, instead of going from t equal to 0 to t continuously through a continuum of different states of the system, we're going to hop over period. And we're going to evaluate the system once a period. So what we're going to get is we're going to start at x0, go to x1, go to x2, go to xn. Let me see, I'll be clearer. We're going to skip a few here. Yeah, so we're going to go to xn and go to xn plus 1. So what's really important here is that we can try and study the chaotic nature of the system by looking at the Poincare section. So we're going to be only interested in the mapping from the previous punch to the next punch. So from the old grapefruit to the new one, and then yet to another one. So these are xn, and this is x plus 1, xn plus 1, this is xn plus 2, and then now we're going to get xn plus 3. So this is the discrete sequence of the states of the system that we're going to be getting in the Poincare section. And the sequence is going to be chaotic. And what's really cool is that by going to this discrete representation of our system, we actually can study much simpler systems than chaotic oscillator. And these discrete, simpler systems will allow us to gain a lot of interesting insight into the transition to chaos. It's literally just a series, mathematically defined, and yet it exhibits chaotic behavior that is very, very similar, strikingly similar to our oscillator. So let's try and take a look at that. Before I do that, let me speed up this movie all the way to the end, after 200 periods, to see what our attractor, strange attractor, looks like. Let's do that. Well, you've done it. You see how we can assemble a strange attractor by running our simulation for a longer time, collecting more and more of the hole punches that our trajectory leaves in the Poincare section. And eventually you're seeing this really nice strange attractor that develops. Some of you have explored the properties of this attractor in great detail, and I hope you had a lot of fun. So now our next step in part 3 of our lecture 9 is to try and understand how does this transition to chaos happen in a much simpler system, which is called a logistic map. That is literally a map of a one-dimensional sequence. And we're going to see you right there. Bye. Hello and welcome to part 3 of our awesome lecture 9, where we are going to be talking about discrete chaotic systems on an example of a logistic map. Logistic map is a really simple discrete sequence. X n plus 1, and this has to be n, not m, to match the book. Let me avoid confusions and use the same notation. X n plus 1, the new element in the sequence, is equal to a constant parameter mu times the previous parameter xn in the sequence times 1 minus that same parameter xn. And here our mu will be between 0 and 4, and x will be between 0 and 1. Okay, so this is the range of parameters and variables for which this mapping works. And this is discrete mapping. So what we do is we go from xn, which we plug in here, and we get xn plus 1. And then from here, we're going to go and plug in xn plus 1 here and get xn plus 2. And so on and so forth. And because this is such a simple mapping, we can actually get a lot of insight into how this sequence of numbers goes chaotic. It has a very similar behavior to the driven pendulum. More specifically, if we were to plot xn versus n, then for mu equals to 2, we would get something that looks like that, where of course there are a bunch of values. It's a discrete sequence. So that is period 1 behavior, because we have gotten onto a constant and nothing is changing. Now, if we were to consider mu equals to 3.1, we're going to get a period 2 behavior. So the larger the value of mu, it's kind of the equivalent of the amplitude of the forcing. We will find something that looks like that. So for every n, every n we're going to get a different number, but there are only 2 different numbers. For even odd n's, the 2 numbers are all the same. So that is period 2 behavior of the system. And finally, there is another example that is shown in figure 312 in the textbook, that for mu equal to 3.8, the behavior is actually chaotic. So what we find, obviously I'm making it up, but you could simulate the system yourself, or you could take a look at figure 312 in the textbook, and it looks something like that, where we no longer have a few select states to jump between like we had in period 2 behavior, or in period 4 there will be 4 states. Here we have a bunch of different states, so we don't quite know at every value of n, the next value of n, where we're going to jump. Of course, it's all deterministic, but if we're just to look at this, it would look random to our eye. So this is the chaotic behavior, and the closer we come to the maximum value of mu, the more chaotic we get. So we start with period 1 system at low mu, we get to period 2 system, and so on and so forth. We're actually going to go through a bifurcation diagram where you could plot the values of x versus the values of mu. And you would find the same exact bifurcation diagram as for a driven pendulum. That's why this is such an interesting system to study, because the system allows us to get a lot of insight into the periodic behavior of the more complicated continuous systems, which we evaluate in phase, just like we saw in the previous part of this lecture. So what is happening here? How does the system go from being period 1 to period 2 to chaotic? If we can't understand what's going on here, there is no hope for us in more complex continuous systems. And so, lucky for us, the system is tractable, so we can actually watch what's happening precisely. So let us first look at the period 1 behavior. So let's plot xn plus 1 versus xn. So let me see. So our xn will go from 0 to 1. Let me get that right. So this would be 0, that would be 1, that will be 1/2. So what we're going to have is a parabola centered at 1/2 with a peak. So this will be 0.2, this will be 0.4. So this is 1/2, this will be 0.2, and that will be 0.8. So we're going to draw a diagonal that is xn plus 1 is equal to xn. We're going to see why we would need that. And then we're also going to draw, and I guess let me use a different color. We're going to draw this curve that corresponds to this mapping. It will look something like that. Okay, so it's symmetric. It peaks at 1/2. Let me mark that this is 1/2, just to be clear. 0.5, and that's xn. All right, and so now suppose that we started with a value at 1/2 over here. And then it means that we would go up and up and up and up. Actually, it's supposed to be a straight line. So we're going to go along this straight line, which is not straight, but it's supposed to be straight. And we're going to get at this value. Then what we're going to do is we're going to go to the left, because we're going to get this value and plug it back in. So from xn plus 1, we need to go back to xn. So that's exactly what we're doing by using this curve, xn plus 1 equal to xn. And we're going to, basically this will be our new value of xn plus 1, which plays the same role of xn, and we're going to evaluate the value over here, and that way we're going to go all the way down. So that's the trajectory. Up, left, down, and we're going to converge onto this fixed point. And at this fixed point, what we get is that x star is equal to f of x star, so that the value of x stays invariant as we go through this mapping. And that is for mu equal to 2. That is the fixed point that we see over here. So what happens when we go to higher value of mu? Mu equals to 3.1. let's try that. So that will actually be 0.8. That will also be 0.8. That will be 1. That will be a straight line. And we're going to draw the curve over here, except that now it peaks at 1/2, which is right here, and it peaks at 0.8. So it's going to do something like this. Okay, it's supposed to be symmetric. So now what we're going to do is start somewhere around here, go up, go over here, go over here, go over here, and we basically are going to get stuck in a loop. So that will be our trajectory. And so what we're going to be doing is we're going to be jumping between these two fixed points. Of which they actually are now not even 2 but 3, because that would be a fixed point as well, except that that is actually an unstable fixed point. If we were to start right next to it, we would run away from it. And if we start somewhere else, we're going to get into this period 2 behavior, where we're jumping between two different values of x. So this, by the way, is xn, and that is xn plus 1, just like it was over here. So how can we understand this sort of period 2 behavior? And for that, what we can do is to go from this mapping from xn to xn plus 1 to go from xn to xn plus 2. So that will be a second iterate. So we're going to switch to xn plus 2 is equal to f of xn. That's what we're going to do. So when we plot the second iterate, it actually looks something like that. So that's our xn plus 2 equal to xn, that's the diagonal, and the second iterate looks like that. Let's see, I'm going to try and hope that I'm going to get it good. Right, ooh, yes. It was supposed to be symmetric, but anyway, that's the best I can do here. So when we draw this curve, we're going to see, well, let me make it a little bit better. So let me make it a little bit more symmetric. Okay, so that's how it can do it. All right. That's as good as I can make it today. Okay, so we're going to have those 3 fixed points, these ones that we're going to see here. Now you can see that these fixed points are actually at the positions where xn plus 2 is equal to xn. And that's not surprising because we have hopped over 2 steps instead of 1. And so in period 2 behavior, we're going to be hopping over the same behavior, either the even or the odd behavior. So that's why we have these fixed points at the intersections with xn plus 2 equal to xn diagonal curve. So these are indeed the 3 fixed points. So you can perform the same exact analysis for period n behavior, where we would get an nth iterate, f of f n times of xn to give you xn plus the iterate, the number of the iterate, and that will allow you to explore what the fixed points are for that higher order iterate of the function. What is really spectacular is we can try and understand the behavior of this mapping by expanding the function f, by expanding the first iterate around the fixed point, around this one. Let's take a look at it and see in which cases the fixed point is stable and when it becomes unstable, just like here. So for that, we can write down that xn is xn plus 1 is equal to f of x star, which will be our fixed point, plus delta x. So that is nothing but xn. And using Taylor expansion, we can approximately write this down as f of x star, which will be just x star because it's a fixed point by the definition of x fixed point, plus f prime at x star times xn minus x star. And what we are going to get from here, let me erase this, is that xn plus 1 minus xn divided by xn minus x star, and of course I don't know what I'm writing here anymore. This should be x star as well, right? Xn plus 1 minus x star divided by xn minus x star. And we're going to take the absolute values on both numerator and denominator. That is going to be equal to the absolute value of f at the fixed point at x star. So that actually tells us that in order for the fixed point to be stable, that is the next value in our sequence, xn plus 1, should be closer to the fixed point than the previous one. So this ratio should be less than 1. Therefore, the derivative, or the absolute value of the derivative, should be less than 1. So then a fixed point is stable. And that is the condition for our fixed point to actually be stable. And so at the point, no pun intended, when this condition no longer holds, our fixed point loses its stability and period doubling happens. So the solution runs away from the fixed point and establishes two new fixed points with period 2 behavior. And so that means that the behavior of this derivative in the vicinity of the fixed point determines how the transition to chaos happens. And this is precisely what was investigated by Feigelbaum in 1978. He looked at this universal transition to chaos because almost any system can be represented through its Taylor expansion. If Taylor expansions look similar, then all of the systems can have a chance to show universal transition to chaos. And that is the idea that you can almost always expand the system around the fixed point as long as the function is smooth. And you can that way establish the universality of the transition to chaos. So that's all I'm going to tell you about this today. Thank you so much for the attention. I hope this was fun. And I'm going to see you in lecture 10, where we're going to start completely new topics of waves. I'm going to get to talk to you about that. Super excited about this. See you very soon.